Welcome to Section 1, Lesson 5. In the previous lesson, we covered the three multiplicative exponent rules, the ones that handle products and powers of products. Today, we round out the picture with the three remaining rules, the ones that handle division, the zero exponent, and negative exponents. By the end of this lesson, you will have all 6 exponent rules at your disposal, and any exponent expression you ever meet can be simplified to a clean form using only these 6 rules. The good news is that all 3 new rules follow from the rules you already know. The quotient rule is just the product rule applied in reverse. The zero exponent rule falls right out of dividing a power by itself. The negative exponent rule is what the quotient rule produces when the bottom exponent is larger than the top. So if you understood Part 1, Part 2 will feel like the natural continuation it actually is. First idea on the board. When you divide two powers of the same base, you sebitirasi the exponents, you do not divide them. So x to the 7th divided by x to the 4th equals x to the 3rd, because 7 minus 4 equals 3. The reason is the same kind of geometry that gave us the product rule. The bottom of the fraction cancels its share of x factors against the top, leaving a smaller power of x. Second idea. Any non-zero number raised to the 0 power equals 1. 2 to the 0 is 1. 5 to the 0 is 1. Even very large or very small bases raised to the 0 power all give the answer 1. The reason will fall right out of the quotient rule when we try to divide a power by itself, like x cubed divided by x cubed. A negative exponent flips the base into a fraction, so x to the minus 3 equals 1 over x cubed. The minus sign on the exponent is the cue to flip the base, and the exponent's magnitude becomes the new exponent on the bottom of the fraction. This rule completes the picture by telling us what to do when subtraction in the quotient rule produces a negative number. Without it, half of all algebra simplifications would simply hit a dead end at the first negative exponent. With it, every result stays in a clean closed form, ready for the next operation. Look at the expression x to the 5th divided by x squared. We expand the top into 5 factors of x, and the bottom into 2 factors of x. 2 of the x on the top cancel against the 2x on the bottom, leaving exactly 3x left over on top, which is x cubed. The general rule is that whatever exponent appears on the bottom subtracts from whatever exponent appears on the top, and the result is a single power of the same base. Generalizing that example gives the quotient rule. For any base x and any exponents a and b, x to the a power divided by x to the b power equals x to the power of a minus b. The exponent subtracts top minus bottom and the base stays the same. This is the third of the 6 exponent rules, and it works exactly the way the product rule did, only with subtraction in place of addition. Now consider what happens when the top and bottom are the same power. Take x cubed divided by x cubed. Anything divided by itself equals 1, so the value of this fraction is 1. But if we apply the quotient rule, we get x to the power of 3 minus 3, which equals x to the 0. Both readings of the same expression must agree, so x to the 0 must equal 1. The zero exponent rule is a direct consequence of the quotient rule. Here is the formal statement. Any non-zero number raised to the 0 power equals 1. We exclude the case x equals 0 because 0 divided by 0 is undefined and the underlying derivation breaks. Every other base, whether positive or negative, large or small, integer or fraction, raised to the 0 power equals 1. Memorize this rule, it shows up everywhere in algebra and in calculus. Now look at what happens when the bottom exponent is bigger than the top exponent. Take x squared divided by x to the 5th. The quotient rule gives x to the power of 2 minus 5, which is x to the negative 3. But we can also see geometrically that 2x on top cancel 2 of the 5x on the bottom, leaving 3x on the bottom, which is 1 over x cubed. So x to the negative 3 equals 1 over x cubed. Both readings have to agree. Generalizing that gives the negative exponent rule. for any non-zero base x and any positive integer n, x to the negative n equals 1 over x to the n. The minus sign on the exponent is the cue to flip the base into a fraction, and the magnitude of the exponent becomes the new exponent on the bottom of the fraction. This is the sixth and final exponent rule, and together with the previous 5 it lets you simplify any exponent expression you ever meet. Here is our first worked example, applying the quotient rule. The expression at the top is x to the 7th divided by x to the 4th. Same base on top and bottom, two different exponents, perfect for the quotient rule. Step 1. Apply the quotient rule by subtracting the bottom exponent from the top exponent. The expression simplifies to x to the power of 7 minus 4. The base stays the same. The operation in the new exponent is subtraction, top minus bottom. Step 2. Compute the subtraction inside the exponent. 7 minus 4 equals 3, so the expression simplifies to x to the third power. Step 3. Verify the answer by expanding both the top and the bottom into factors of x. The top has 7x's multiplied together. The bottom has 4x multiplied together. Cancel the 4x's on the bottom against 4 of the 7 on the top, leaving 3x left over. Step 4. 3x's multiplied together is exactly x cubed. Same answer the rule gave us. The geometric expansion and the rule agree, which is exactly what we want every time we use a shortcut. Always being able to fall back on the expansion is what makes the quotient rule trustworthy, even when the exponents are large enough that you would never want to write out all the factors in practice. So the answer is x cubed. The lesson from this example is that the quotient rule is just a fast shortcut for the cancellation of x factors between the top and bottom of a fraction. Whenever you see same base division, subtract the exponents and skip the manual cancellation. The big speed up arrives when the exponents are large, like x to the 100th divided by x to the 97th, without the rule that requires writing out 100 x's and crossing off 97 of them. With the rule, you just compute 100 minus 97 equals 3 and write down x cubed in seconds. Here is the second worked example. This one combines the product rule, the quotient rule, the zero exponent rule, and the negative exponent rule all in one expression. The expression at the top reads x cubed times x to the negative 5, all divided by x to the negative 2. We are going to simplify it down to a single number. Step 1. Combine the two factors on the top using the product rule. The product rule says add the exponents when the bases are the same, so the top becomes x to the power of 3 plus negative 5, which simplifies to x to the negative 2. The full fraction now reads x to the negative 2 divided by x to the negative 2. Step 2. Apply the quotient rule by subtracting the bottom exponent from the top exponent. Negative 2 minus negative 2 equals 0, so the expression simplifies to x to the 0 power. Be careful with the double negative. Subtracting a negative is the same as adding a positive. Step 3. Apply the zero exponent rule. Anything raised to the 0 power equals 1 as long as the base is not 0, so the expression collapses all the way down to the number 1. Step 4. Verify by going through the negative exponent rule explicitly. Rewrite x to the negative 5 as 1 over x to the 5th, and rewrite x to the negative 2 as 1 over x squared. The original expression becomes a fraction whose numerator is x cubed times 1 over x to the 5th, and whose denominator is 1 over x squared. Working through the arithmetic gives x squared over x squared, which equals 1. So the final answer is 1. The big takeaway from this example is that all 6 exponent rules cooperate. Once an expression is built only from products, quotients, and powers of the same base, you can chain the rules in any order and always reach the same correct answer. The order you choose only affects how much arithmetic you do along the way. The final answer is always identical. In practice, work from the innermost grouping outward, simplify within each group first, and the chain of rules unfolds smoothly. A useful sanity check after every chain simplification is to substitute a small concrete value for the variable, like x equals 2, into both the original expression and the final answer. Both should evaluate to the same number. If they do not, one of the rules was misapplied somewhere in the chain, and you can trace through the steps backwards to find the slip. This substitution check has saved countless students from wrong answers on midterms and finals, and it costs only a few seconds of arithmetic to perform. 3 common mistakes students make when applying the new exponent rules. Each one comes from confusing one rule with a different operation that looks visually similar. First mistake: a student forgets to subtract and instead divides the exponents. They write x to the 7th divided by x to the 4th equals x cubed divided by x cubed. The 7 and the 4 became a separate division. That is wrong. The quotient rule says subtract the exponents, not divide them. The correct simplification is x to the power of 7 minus 4, which equals x cubed. Second mistake: a student writes that any base raised to the 0 power equals 0. They write 5 to the 0 equals 0 because of a vague feeling that 0 exponent should give 0. That is wrong. Any non-zero base raised to the 0 power equals 1, not 0. The proof comes from the quotient rule applied to a fraction whose top and bottom are equal. Third mistake: a student thinks that a negative exponent makes the base negative. They write 2 to the negative 3 equals negative 8. That is wrong. A negative exponent flips the base into a fraction. It does not negate the base. The correct value is 2 to the negative 3 equals 1 over 2 cubed, which equals 1 over 8. The new exponent rules unlock 4 real-world contexts: scientific notation, half-life, decay, asset depreciation, and signal attenuation all rely on quotient or negative exponents to express their core formulas compactly. First, scientific notation: 1 nanometer equals 10 to the negative 9th meters. The negative 9 in the exponent counts how many decimal places we shift the leading digit to the right of the decimal point. Negative exponents make scientific notation usable for very small quantities like atomic radii, gene lengths, and the wavelength of visible light. Second, half-life decay: the mass of a radioactive sample after n-half lives equals 1/2 raised to the n power times the original mass. The fraction 1/2 is exactly 2 to the negative 1, so each half-life multiplies the remaining mass by 2 to the negative 1. After 10 half-lives, the remaining mass is 2 to the negative 10, or 1 part in 1020, 4 of the original. Third, asset depreciation: a car or a piece of equipment that loses 15% of its value every year retains 0.85 of its value each year. After n years, the value is the original value times 0.85 raised to the n power. Repeated multiplication by a fraction smaller than 1 is exactly what the product rule lets us simplify when we need to combine 2 depreciation periods into one. Fourth, signal attenuation: the power of a Wi-Fi signal at distance d from the router is approximately the source power divided by d squared. We can also write that as the source power times d to the negative 2. The inverse square law is just a negative exponent in disguise, and it shows up everywhere from radio waves to gravitational fields to camera flash. 3 things to take with you from this lesson before we move on to scientific notation in the next lesson. Each rule will come back constantly through the rest of the algebra course, especially in factoring, in rational expressions, and in exponential functions. First, when you divide 2 powers of the same base, subtract the bottom exponent from the top exponent. X to the a divided by x to the b equals x to the a minus b. Same base on top and bottom is the trigger for this rule. Second, any non-zero base raised to the 0 power equals 1. The proof is direct: dividing any non-zero quantity by itself gives 1, and the quotient rule turns that into x to the 0. 5 to the 0, pi to the 0, even negative 2 to the 0, all give the answer 1. The only excluded base is 0 itself, because 0 divided by 0 is undefined and the derivation breaks down at that single point. Third, a negative exponent flips the base into a fraction, x to the negative n equals 1 over x to the n. The minus sign on the exponent is the trigger to flip, and the magnitude becomes the new bottom exponent. The minus sign never makes the base itself negative, it only signals the flip. With these 3 rules added to the 3 from Part 1, you have all 6 tools needed to simplify any exponent expression to a single clean form. The 6 rules are product rule, power of product rule, quotient rule, zero exponent rule, and negative exponent rule. Together they cover every situation where same base exponents meet under multiplication, division, or stacked powers, and they always reduce a complicated expression to a single power of a single base. Without these rules, every algebra expression involving exponents would have to be evaluated symbol by symbol, which would slow down nearly every formula in physics, chemistry, finance, and engineering. With them, exponent arithmetic becomes as fast as integer arithmetic. Coming up next, the lesson called scientific notation, where negative exponents do the heavy lifting for very small numbers in chemistry, physics, and engineering, and where the rules from these 2 lessons let you multiply and divide tiny numbers without losing your place in the decimals. Scientific notation is essentially the most useful single application of exponent arithmetic in the whole technical world, and it relies on every one of the 6 rules we just covered.